Good day. Professor Van here. This video discusses control methodology. Control methodology is the application of control theory to design systems with desired behaviors in control environments. We'll be discussing four kinds of controls. First is the on-off control. This is the simplest one. Second is the sequential control. Third is the PID control. And lastly, we'll discuss about the program control. On-off control. On-off control is the simplest form of feedback control. An on-off controller simply drives the manipulated variable from fully closed to fully open, depending on the position of the controlled variable relative to the set point. Due to the switching logic, an on-off controller is often called a bang-bang controller or a two-step controller. As an example, let's take the temperature control of an industrial oven. The temperature inside the oven is measured with a sensor and feedback to the controller. Based on the error, which is the difference between the set point temperature and the measured temperature, the heating elements are turned on or off by the controller. There are no intermediate values of the heating element. They are either fully on or fully off only. If we compare this system with the generic closed-loop system explained before, we can identify the following elements. First, the controller is the switch, the plant is the oven itself, and the feedback or the measured output is the temperature. The industrial oven has two important characteristics which needs to be explained because they affect the response of the controller. First is the dead time, and second is the capacitance or inertia. In most of the control systems with feedback loop, the system cannot respond instantly to any disturbance and it takes time or delay until the controller output has an effect on the measured plant or output. This time delay is known as dead time. In the case of the industrial oven, if the access door is opened, it takes time until the temperature drops, the controller senses the difference, turns the heaters on, and the temperature is brought back to the set point. Dead time has the effect of hiding the disturbance from the controller and limits its ability to react quickly. The capacitance of a system is seen as the resistance to changing inputs. The higher the capacitance of a system, the longer the time it takes to react to changes. With the oven cold, even if turning the heaters on, it takes time for the temperature to start increasing and reach the nominal value. The advantage is that the capacitance has the tendency to filter or dampen the effect of disturbances on a system. In the theory of control systems, the industrial oven is defined as a first-order process with dead time. The transfer function of a first-order process with dead time is given below. Its h of s is equal to k divided by t times s plus 1 times e raised to negative tau times s, wherein k is the gain, t is the time constant, and tau is the dead time. Now let's assume that the set point temperature of the oven is 120 degrees Celsius, and the initial temperature is 0 degrees Celsius. When activated, the controller will sense the temperature difference via the temperature feedback and switch on the heating element. The rise in temperature is not abrupt but slow, and it takes around 300 seconds until the temperature reaches the set point value. When the temperature is higher than 120 degrees Celsius, the controller switches off the heating element. Since the heating element are still hot, the temperature will continue to rise for a short time, followed by a decrease. When the temperature goes below 120 degrees Celsius, the on-off controller switches on the heating element. Since it takes time for the heating element to reach the nominal temperature, the temperature in the oven will still decrease for a short time, followed by an increase. As you can see, the on-off controller cannot keep a steady temperature in the oven but always goes above and below the set point value. This cycling around the set point value is called hunting. The response of an on-off controller can be summarized in the image. When the error is positive, the controller is switched on. When the error is 0 or negative, the controller output is switched off. We can see how the on-off controller is switching the output from on to off around the set point value. The constant switching with high frequency around the set point can lead to stress on the actuators and potential failure. For this reason, most of the on-off controllers have an integrated hysteresis. The on-off controller with hysteresis will not switch around the set point, but between an upper and lower limit. The frequency of the switching will decrease, but the variation, or the overshoot, around the set point will increase. The error is not anymore compared against 0, but against a hysteresis value. The higher the hysteresis value, the lower the switching frequency, which is what we want. But the downside is that the overshoot will be higher, which is something that we don't necessarily want. For our particular example, if the oven is set to a temperature of 120 degrees Celsius, this is the set point value, and the hysteresis to 20 degrees Celsius, the on-off controller will switch off when the temperature is higher than 130 degrees Celsius, no longer 120, and switch on only when it is less than 110 degrees Celsius. The controller switching frequency has decreased, but the variation of the temperature, or the overshoot, around the set point has increased. In practice, for a particular application, the hysteresis is set in order to get the best compromise between switching frequency and overshoot. Instead of a hysteresis, an on-off controller can also have a deadband. The deadband represents the lower and upper limits of the error between which the controller doesn't react. In this case, the controller will have 3 states. As an application, we can imagine an electric motor, which needs to position roughly a component between some limits. The on-off controller will rotate the motor forward, backward, or wait. If the position of the component is between the deadband, the controller will be in the idle state. The main advantages of an on-off controllers are simplicity, inexpensive, and digital output because it only has 2 states. The main disadvantages are the controlled parameter will continuously switch around the set point, and if the hysteresis is not set correctly, the deviation from the set point could be quite significant. On-off control is primarily used in non-critical applications, where the error between the set point and plant output can vary with a relatively large amount. For example, temperature control systems for houses, freezers, and other home appliances are using on-off control. The next control is sequential control. This is a control system in which the individual steps are processed in predetermined order. Progression from one sequence step to the next being dependent on defined conditions being satisfied. Such a system may be time-dependent, in which the step transition conditions are functions of time only, or it can be an external event dependent, where the conditions are functions of input signals only, or combinations of these, and perhaps more complex conditions. Next control is what we call the PID control, or proportional integral derivative control. A PID controller is the most common control loop feedback controller used in a control system. To explain this, let's start with the classical system block diagram. Set point or in some reference, we call it the reference input, is the input value we want the process variable. The process variable is sometimes called the output. So the set point is what we want the process variable to be. For example, think of your heating system in your home. We want the room to be at 25 degrees Celsius. So we give our system 25 degrees Celsius as the set point or input. The system tries to regulate the process variable or output to have a value as close as 25 degrees Celsius as possible. PID controller looks at the set point and compares it with the actual value of the process variable through sensors in the room and sees how close it is to 25 degrees Celsius. If they are the same, PID controller does nothing and the controller output is 0 because the goal is already reached. But if there is a difference between the set point and the process variable, in other words, there is an error that is not 0, a corrective action is taken by the controller to reduce this error. Let's adapt the analogy of changing lanes on a freeway on a windy day to the block diagram given. We are the driver and therefore the controller of the process of changing the car's position. Notice how important closing the feedback loop is. If we remove the feedback loop, we would be in an open loop control and would have control on the car's position with our eyes closed. So as you can see, a closed loop control is very important. The operation of PID controller box is quite complex. The PV or process variable is subtracted from the SP or set point to create the error. This error is multiplied by 1, 2, or all of the calculated P, I, and D actions, depending on which ones are turned on. Then the resulting error X control actions are added together and sent to the controller output. So we can only turn on P or I or D. Or sometimes we can even combine P and I but not D. P and D, or even we can use everything, P, I, and D all together. Proportional control, this is the P only. If we've enabled proportional control, this is the block diagram of the controller that we will have. In proportional only mode, the controller simply multiplies the error by the proportional gain, Kp, to get the controller output. The proportional gain is the setting that we want to tune to get our desired performance from a P-only controller. Integral control. The integral of a signal is the sum of all the instantaneous values that the signal has been from whenever you started counting until you stop counting. So if you are to plot your signal on a trend and your signal is sampled every second, and let's say you are measuring temperature, if you were to superimpose the integral of the signal over the first 5 seconds, it would look something like this. The green line is your temperature, the red circles are where your control system has sampled the temperature, and the blue area is the integral of the temperature signal. It is the sum of the 5 temperature values over the time period that you are interested in. In numerical terms, it is the sum of the areas of each of the blue rectangles. The integral turns out to be the area under the curve. When we have real-world systems, we can actually get an approximation to the area under the curve, which, as you can see from the diagram, gets better the faster we sample. In integral-only mode, the controller simply multiplies the integral of the error by the integral gain, or Ki, to get the controller output. Derivative control. Derivative is just a mathematical term meaning rate of change. In derivative-only mode, the controller simply multiplies the rate of change of the error at that instance by the derivative gain, KD, to get the controller output. The tricky thing about PID controllers is that to tune Kp, Ki, and Kd to suitable values to have a good controller. The other thing is to use correct components of P, I, and D according to your application or system. Let's have another example of PID control. Suppose you have a car that you want to place in a position X, or this is our output position or process variable. And we can sense the current position of the car, and we also know the initial position of our car. So if we were to apply PID control for this car, the proportional gain, Kp, means that the electricity you apply to the motor is proportional to the error. Big error in position means big electricity to correct it. If the proportional gain is too low, the car just moves slowly. If you keep increasing the proportional gain, it moves faster, but eventually the car zooms past the target position and then runs back and forth several times, eventually stopping near the target. This is why you need derivative gain, Kd. Derivative gain means that if you have error, but the error is quickly going down, then you can decrease the electricity applied to the motor a little bit. This prevents zooming past the target and helps you stop at or near the target location. But even with the proportional gain, Kp, and derivative gain, Kd, your car will never actually land exactly on the target position. Because even if you are close, such a small error won't make enough electricity to move the car at all. To solve this problem, we keep track of the accumulated error over time and use that to add some electricity so that the car doesn't stop short of the target. This is called the integral gain, Ki, and it will ensure that you actually move all the way to the target location. Lastly, we have program control. Program control is how a program makes decisions or organizes its activities to manipulate objects. Program control is used for highly complex systems. For an example, let's take a look at an engine. It's a type of electronic control unit that controls a series of actuators on an internal combustion engine to ensure optimal engine performance. It does this by reading values from a multitude of sensors, not just one, but a multitude of sensors within the engine bay, interpreting the data using multi-dimensional performance maps called lookup tables, and adjusting the engine actuators.